Shane Geary. Now, Pragmatic is a rising star in the UK semiconductor industry, but you don't make semiconductors the way most people think of them, silicon chips. It's not that, is it? Tell us what you do.
Well, we have a unique approach to semiconductor manufacturing. We don't use silicon. Over my shoulder here, you should be able to see a 300 millimeter wafer, but it's a glass wafer. So our unique approach to semiconductor manufacturing is to use a 300 millimeter glass wafer and to coat it with a very, very thin polymer coating. And on that, we deposit our semiconductor material and we go through some very familiar semiconductor processing steps to form our ICs. But some of the real magic that happens after we're finished the wafer manufacturing and we essentially peel off that very thin polymer coating. And if I show here, we're left with a very thin foil of our flexible ICs, thinner than paper thin. And we mount that securely on a wafer frame and send that to customers. So, very different than silicon. It is semiconductors, it is integrated circuits, but on very, very thin, very, very flexible, and very, very low cost manufacturing process.
So that means that obviously bendy. You can put it on anything that any material you like, really, can carry its own integrated circuit and all the information you want to put on there.
Well, that's exactly it. So any of your audience, if they're presented with the unique advantages of very thin, very flexible, very low cost, they'll immediately come up with a huge variety of potential applications. Our vision is to put our integrated circuits in 1 trillion items over the next decade. And
do you mean that? Do you mean that? 1 trillion?
That is genuinely our ambition. And when they're really low cost and very environmentally sustainable and flexible, so you can add these flexible ICs to smart packaging of devices. So, for example, to enable a flexible and circular economy, to enable recycling of goods, of packaging, adding some of these really, really low-cost ICs enables all that. So that then rapidly gets us up into the tens, hundreds of billions and into the trillions of items over the next decade or so.
Can we identify what you mean by low cost? I mean, I'm assuming that what you mean is something that's almost negligible when you compare with the price of, say, a bottle or a cardboard box or an item.
And that's exactly it. And not so much the unit cost of that bottle itself, but its entire life cycle cost, and enabling the added value of true recycling. I think in the context of that overall cost and overall value, absolutely, the return on investment of integrating something like a FlexIC into pretty low cost devices and objects is absolutely something that some of our customers are really, really excited about. And I think this can only be done with the very low cost technology we have. And we talk about, we can build wafer fabrication lines at a tiny fraction of the cost of an advanced silicon wafer fab. And that then at really high levels of productivity and really optimized manufacturing process allows us to make ICs, flexible ICs at very low cost.
Now, anybody you're running a factory, a warehouse, or whatever will be familiar with RFIDs. Does this replace the RFID which people put on stock parts, on bins, and so on?
Well, indeed, it enables RFID, because one of the key applications of our flexible ICs, if you bond this to an antenna, if you design an RFID chip using our flexible IC technology and bond it to an antenna, now you have a very low cost RFID tag that's flexible, and I think really will help enable RFID and NFC use cases in a much broader set of use cases than currently. So I think it's very much part of enabling RFID market to grow in the long term.
Now, obviously, as the net zero legislation, the regulations, the obligations on the part of an increasing number of manufacturers, all the way to small manufacturers eventually, is going to mean that people have got to be aware of scope 1 and 2 is fair enough, but scope 3 emissions, every identifiable part of their supply chain, they're going to have to report the carbon element of what they do. I'm assuming that this plays right into assisting that.
Well, it absolutely does, and also a term that's beginning to grow in usage is scope 4, which is replacing downstream applications and devices with something which is much cleaner. So I think if we allow our FlexICs to replace silicon ICs, that's another source of saving in the world that some people are calling scope 4. But so we have a very, very compelling sustainability message. And I'll start with scope 1 and scope 2. We have a manufacturing process that is extremely optimized and efficient. And we have absolutely stripped that process down to the minimum number of steps that delivers the maximum value. And so, we can add that together with the fact that our ICs are very thin and flexible. That says we're using very little material. And we don't have some of the long, high temperature process steps that you have in silicon. We use a fraction of the gases and liquids and water and chemicals. We have, per IC or per square inch of silicon, in silicon case or the FlexICs in our case, we use a small fraction of the energy, small fraction of the water. So as a sustainable manufacturing enterprise, we are orders of magnitude more efficient than a silicon fab, which just has to consume so much energy and so much water and so much toxic gases and chemicals. And our process is just so fundamentally more sustainable.
Before we get further into that, just a quick question, because you talked about maybe your FlexICs beginning to replace applications where currently silicon chips are being used. We haven't mentioned the power potential, the computing power potential of FlexICs. We've kind of assumed they're pretty basic, but what's the potential in there for future usage?
Yeah, so I don't think our big advantage here is necessarily replacing silicon like for like, by the way. So when we're talking about getting into 1 trillion devices over the next, or 1 trillion objects over the next decade, that really was never going to be where silicon was going to play anyway. So it's really the adjacent and new markets and new application areas that's where we really think we're enabling. But the surprising amount of compute capability possible in our FlexICs, even though geometries are larger than leading edge silicon. We published a Nature paper where we have a 32-bit ARM processor implemented in an older generation of the FlexIC process, and we just published another Nature paper where we've implemented a machine learning algorithm on a very, very small, low-power circuit core on FlexICs. So very, very widespread applications, and in fact, one of our key strategies here is to make our process available to the outside world, like a foundry, make our PDK, our process design kit, available to customers for them to innovate and design onto our FlexIC process. And then you've innumerable examples of what could be achieved using our customers' innovative IC design capabilities once we make these processes available to customers.
One of the developments that's being managed by the High Value Manufacturing Catapult and by the Advanced Manufacturing Research Center, AMRC in particular, is to develop what they call the digital thread, which means that data, non-proprietary data, but data can follow a product from the design process, entire life cycle, all the way through to disassembly across the entire range of manufacturing. I imagine that the FlexIC could marry into that intention, that paradigm very easily.
Well, I think that's exactly the use case we're talking about, because you want to have a really flexible form factor. You want it to be conform to whatever the traceability requirements of whatever materials you're talking about. You want some memory capabilities. You want some compute capabilities. You want to be able to read it, something like NFC or RFID. And that implementing that level of traceability, what we call item level intelligence, right through the manufacturing supply chain, whether it's expensive goods, whether it's fast moving consumer goods, whether it's food, whether it's pharma, this ability to implement traceability entirely through the full product life cycle. I think marries well exactly to the capabilities of our FlexICs and the form factor that we deliver and the cost that we can deliver.
Thinking about it, you could have multiple FlexICs inside a product. I mean, a car, for instance, multiple bits, aeroplanes. So the traceability and origin, provenance of parts has always been a problem. Blockchain has helped that, but this will really assist in identifying the origins of parts, and of course, as you've just said, tracing everything from start to finish.
That's exactly it. And there are some industries where this is a big challenge because you may ship in bulk from your manufacturing location, and then you take that bulk supply and you split into small lots, and then you distribute it to customers. So take, for example, pills being shipped from a pharma plant, and they ship in large boxes and in bulk, and they get split into small boxes and distributed to pharmacies. And so maintaining that traceability all the way through the life cycle and distribution of that product as it gets split from a large bulk supply to small individual packages, that does require this low cost smart packaging. And that is exactly the type of use cases that FlexICs are perfect for.
I know that actually the NHS, healthcare generally, is a big play for you, isn't it? I mean, it's not just about pills. This could apply throughout the healthcare system.
Well, I think it could, and there's lots of healthcare use cases. And I give that challenge to some of your listeners about if you're presented with these really low cost, flexible, thin ICs, what could you do with them? And some of the medical applications in the future could be, for example, around smart patches that you can stick on your body that need to be flexible, need to be able to conform to your skin, need to have some memory, need to have some compute, need to have some sensing. That is a perfect application for FlexICs. So many medical applications, quite beyond the traceability of pills and medicines.
You talked about working with customers on their projected use cases, asking them to come up with ways in which this could be used. But you also have your fab in a box as a service. Tell us a little bit about that, because I thought fabs were pretty, you couldn't move them around. They're sealed units, clean rooms, the whole thing. You're talking about doing all this in a box that can be moved.
Yeah, so it's a very, very small clean room area. We like to say that, the minimum viable silicon fab is likely tens of thousands of square meters of clean room space, and a very, very large construction project costing many, many billions of dollars. Our capital expenditures are 1/100th of that scale. Our size of our clean rooms is less than 1/10 of that size. So our minimum viable wafer fab, a mini fab, is only a few hundred square meters and can be put into essentially a brownfield site, a warehouse, or beside some of our integrated into our customers' manufacturing sites. Doesn't need the massive amounts of power, water, natural gas, etc., that needs to be supplied to a major silicon fab. So we can essentially put this fab in a box in any medium-sized warehouse that has a few hundred square meters of empty space. and takes very little construction. So that is a unique ability that we have, and it really because of our very, very simplified process, which, as I mentioned, very high productivity, very high throughput per square meter of clean room, very low levels of material usage. So we can manufacture a lot of ICs, a lot of output from very little inputs. And that's what allows us is to put this small fab in a box in essentially any location where there may be an existing brownfield site, existing manufacturing site, or an empty warehouse.
You're really upending the semiconductor industry. How many other companies are there out there globally doing what you're doing?
We would say none. I don't think there's any company that has the combination of the technologies, the flexible ICs made in the type of way that we do it at the low cost and the sustainability levels that we have, and that can package this up into a fab in a box and run a distributed manufacturing model. I think we do leverage the broader semiconductor industry very much so. I mean, we use relatively standard clean room equipment, so it's about repurposing standard semiconductor manufacturing equipment towards a very, very unique process. So the mini fabs that we build are very recognizable to anyone in the semiconductor industry. They recognize the tools, they recognize the process steps. But the unique bit is the materials and the process flow that we use. And we think that combination is truly unique in the industry.
Clearly, there are going to be people who are going to ask the question, we saw what happened to ARM, we saw what happened to Newport Fab. Newport Fab, it got a bit mixed up because the government had to step in and stop one element of the buyout, and eventually went to an American bidder. ARM is no longer British. What about Pragmatic? I know you've had £60 million of investment from the UK Infrastructure Bank, which means that the government, the nation, has gotten behind you. Can we hope that Pragmatic will stay in the UK as a UK company?
So we're very, very proud of our UK heritage. And we've got the first 300 millimeter semiconductor manufacturing plant in the UK. We've invested very heavily in the UK, and we have the majority UK investors. We have a very, very aggressive investment plan for the UK to expand our 300 millimeter manufacturing line in the Northeast over the next several years. So we're very committed to the UK. We're very proud of our UK heritage, and don't see that changing. And, we see ourselves as a UK and UK-based company.
Well, Shane Geary, good luck to you. Thank you very much for being on the production line.
Great to talk to you, Nick.